In this first module, I'll be talking a little about how to prepare the material synthesis, and how to implement them for a study. The three systems I would like to talk about a little these days are basically nickel-based systems with different solid oxides, in which we have developed the studies about how do they interact for activating the CO2 molecule. Okay, the first one deals with some nickel-based systems complemented with zirconium oxide that we put it in carbon nanotubes in order to have the possibility to really identify where the activity comes from, what are the active sites, and how does really the CO2 molecule absorb on the surfaces. As you see in the slides, there are three different systems. In the first one, there is carbon nanotubes, pure carbon, where we put the nickel nanoparticle on it to see how these materials interact with the CO2 molecule by itself, with no other oxide, with no other material complementing the activity. In the second one, you will be able to see some thin layers of zirconium oxides that supports that those are the places where we put now the nickel nanoparticles. In a different way than before you see the nanoparticles were in carbon, in this case are on top of the zirconium oxide. And the third system is a very nice one, and in that one we covered in some sort of a clamshell behavior the nickel nanoparticles surrounded by a crust of zirconium oxide. So as you see, we have three different systems where we can identify really where the CO2 molecule interacts, in which place, or with what kind of solid does it interact, and then we will find how can we measure the activation of that. That was made by basic wet impregnation system using an aqua solution that you immerse the nanotubes on that, and then you can sign the system to get the oxides on top of the carbon nanotubes. The next systems are a different one. It's also a carbon oxide. It's a calcium titanium-based system, what is called perovskites, and then we put the nickel on it. In the picture, you see the basic conformation, the very nice crystals of calcium titanate, or CTO perovskites, that is composed by calcium, titanium, and oxygen. And you will see it's a ceramic type of material, very strong, very stable on temperature, and very, very crystalline. And we use it as a model system for depositing also the nickel nanoparticles on it. But there were used two different systems for that. In the first one, we have the crystals already prepared for the CTO, and we put the nanoparticles on it and see how they interact. And we were even farther on that in such a way that we use a synthesis protocol called salt gel method, in which before preparing the CTO crystal, we already put the nickel precursor on it. So we have a stronger interaction in that system, since the nickel is already doping the CTO material. And the final system I'll be showing you in this module is what we call a graphene oxide system, or modified graphene oxide. That is basically, you took the graphite, yes, carbon graphite, laminar carbon graphite, and you oxidize it to spread out the layers of it, and then by sonication or some acid attacks, you are able to separate different layers of the graphene oxide, what it's called. Okay, it's a sheet of carbon in a hexagonal arrange with a lot of functional groups, oxygenated functional groups, and that's why the name comes from, it's the graphene oxide. And when we have these layers spread out in a solution, what we do is we do an acid attack, a reduction procedure, in which those layers we start removing these oxygenated systems or oxygenated species to get what we call the reduced graphene oxide. It's the closest we can get to the pure graphene layer. Okay, we don't want to get to the pure graphene layer because that doesn't have much catalytic activity itself, So that's why we go only to the reduced species when we still have some oxygen sites on the surface. Then what we do is produce some defects on the layer. As you may know, all the catalytic systems are favored by these defect sites that have the activity on the system. And we do that by a basic attack with sodium hydroxide, producing some defects on it. Then we are able to put some nitrogen atoms in these defects, because we know that nitrogen sites strongly interact with CO2, so we do that in order to analyze what would be the effect of having these strong active sites for CO2 absorption. And finally, as you may expect, we also have to put the nickel on the systems, okay? Because nickel is the site that will provide us the hydrogen for getting the CO2 reduced. So in such a way, we're able to produce a model system. You see, it's a layer with different species, different characteristics on it, that allow us to see what is the effect of each one on the activation of the CO2 molecule.